So I'm Nicole, I'm one of your TAs, and I'm giving this lecture in place of Ryan, who's traveling right now. So I have a tendency to go a little fast. If you feel like I'm moving too quickly, just stop me, please stop me. Or if you don't buy something, that we're asserting, just let me know, okay? So today we're going to talk about some optimization basics. But let's start by reviewing what we did last time. Last time we talked about what makes a set convex and what makes a function convex. And there are many ways to prove that something is convex, right? We can start from its definitions. We went over, what a first order and a second order characterization of a convex function is. But we can also kind of make these proofs simpler by not going to the definitions every time and using the fact that some operations will preserve convexity. So just to kind of see what stuck from last lecture, is this monstrosity at the bottom of the slide convex? Let you think about it for a sec. Okay. Raise your hand if you think it's convex. Okay, luckily math is not decided by majority vote. It is convex. Does someone who is brave enough to raise their hand want to tell me their reasoning?
The max function is always convex.
Sure.
Convex functions. And the function on the left, the log function, is convex. And then the right side, the L1 norm is convex. And if you cube it, it's still convex.
That's correct. Does anyone have a question about any of that logic? It's totally fine. Yeah, log's concave, but then this guy. So the rule is, if it's concave, right, then what does the guy inside have to be, right? Think about when we do log rules, we can pull this 7 out, right? So then it will be -7 log, and then it will be convex. So yeah, we're going to go over this in a little bit, but because you can just multiply by a negative to switch from convex to concave, we sometimes play it fast and loose with those terms. But I know from Piazza that some of you want to be really careful.
Would there need to be any conditions on A transpose X plus B? Like it needs to be greater than 1 or something like that?
No, because, so this guy inside is convex, and then over positive values, right, cube is going to be convex and...
I meant for the log.
Oh, you meant for the log guy. Oh, this guy. Yeah. Sorry, there's too many A's and B's in this one. Sure, I mean, it would need to be in the domain of log, right? It would need to be successfully evaluated by the log. Other questions? Okay, cool. So that's what we did last time. Today we're going to talk about some basic optimization terminology, which actually we've already been kind of using, and talk about what are the properties of solutions to optimization problems. And then we'll go into something that you'll see will be pretty useful throughout the course, which is how can we manipulate optimization problems to make them easier to solve. And sometimes this means making a non-convex problem a convex one. So let's just go over the basic terminology, which I think some of you guys have figured out, right? So I've got minimization over some set D, which is going to be the intersection of the domains of F and G. I want to minimize F. So F is going to be called the objective function. Some of you may see it called the criterion function. I tend to call it the objective. G gives us our inequality constraints. Notice that we got rid of the H notation because we're talking about a convex problem, so H is necessarily affine. We can write it as a system of linear equations. So if X is in the domain, the proper domain of the functions, and it satisfies these inequalities, we call it a feasible point. We've already been using this term. And then the function value, the value of F, that is the minimum over all of the feasible points, is going to be called the optimal value. So if we've got a feasible point X, and it achieves the optimal value, that's a solution. You can see there's many ways to call it, but we'll refer to it as a solution to the problem. And if it's away from the optimal value by epsilon, we're going to call it epsilon suboptimal. And this concept is going to come back when we talk about the convergence rates of various methods, like gradient descent. A note here, just for being super careful, in this class, we're not going to worry about whether or not an optimization problem has a solution. Naturally, you can imagine that convergence rates for a particular algorithm that's trying to solve the problem will not hold if the problem has no solution. But throughout the course, we're just going to assume that the problems we're working with have solutions. Okay? So some other terminology that I think has come up on your homework maybe is that if we have a feasible point and our inequality constraint achieves equality, then that inequality constraint is active at that point. Okay? And then I think the last thing, and I kind of mentioned this on the previous slide, is that you can always go between convex minimization and concave maximization. And sometimes it might be nice for the semantics of the problem to be in one mode versus another, but this switch is really easy to do. Are there any questions about this?
What is the asterisk?
Pardon?
What is the asterisk?
F star is the optimal value. So it's the minimum value of f of x, where x is in the set of feasible points.
Can you explain intuitively what active means?
Yeah, sure. So these inequality constraints are less than or equal to, right? So you can think about it as you have some boundary, right? And you want to make sure that your feasible point is on the other side of this boundary or at the boundary, right? So if an inequality constraint is active, then that means that your feasible point is at the very edge. And if you're kind of familiar with the simplex algorithm, right, you're kind of you're always at an active edge when you're solving that. But the other intuition, I guess, and this we'll talk about this later, is that if it were not active, then it would be possible to get a better x, right? And that's usually what happens. That's usually how you can reason that an inequality constraint must be an equality at the solution, right? And this, I think this is also kind of on your homework. Are there other questions? Okay, cool. So let's talk about the set of all solutions to an optimization problem. This is going to be a convex set. And I think the proof is kind of outlined there, but we can go through it bullet by bullet. So firstly, if x and y are solutions, right, the domain over which we are minimizing is a convex set. So naturally, their convex combination is going to be in the set. G is a convex function. So naturally, theta x plus 1 minus theta y is going to still satisfy our inequality constraint. And then we have an affine constraint, right, affine equality constraint. And that, too, is going to include our convex combination. So if f is convex, then we can have, by the same argument we used for g, we can see that we will still obtain the optimal value, f star, if we input a convex combination of the two solutions we already have. So the other thing to think about is that if f is strictly convex, this is going to be a set of one element, right? There's going to be only one solution. And the reason that is actually that this last bullet point, actually we can do a formal proof, right? Let's do a proof by contradiction. Okay, so x and y are solutions. Can you read my handwriting, by the way? Okay, cool. Okay. So since we know that the set of solutions to a convex problem is going to be convex, this guy must also be a solution, right? In a world where we have multiple solutions for a strictly convex f. However, when I go to this fourth bullet point, right, my inequality has now become strict. So if x and y are both solutions, this side is going to evaluate to f star. If this guy is also a solution, this is going to evaluate to f star. And that's a contradiction. Okay? So set of solutions is a convex set, And if F is strictly convex, if we're that lucky, there's a unique solution. Are there any questions about this? Okay, great. So here's a problem that a lot of you are probably familiar with, and we're going to look at it through the lens of the terminology that we just learned. This is the lasso problem. So what we've got in our objective is what? Someone want to tell me what the objective of this is? Of this problem? Just raise your hand. Pardon?
Least squares.
Least squares, that's right. So our objective function f is that least squares term at the top. What's the inequality constraint? It's pretty obvious, right? It's that L1 term. Are there equality constraints? No. Okay. So is this problem convex? Yes, right? Yes. In fact, we've solved it all the time. Okay. So let's talk about now when it's got a unique solution. Because our objective function is theoretically strongly convex, maybe, right? So in what scenario do we necessarily have a unique solution to this problem? There's two scenarios on there, right? When X is kind of a tall, skinny matrix with full rank, right? And then when X is kind of this wide matrix that definitely does not have full column rank. So in what case do we necessarily have a unique solution? Shout it out. First one or second one? First one. Okay, thank you. All right, so is it possible to get a unique solution in the high dimensional case? Does anyone know? Do you want to answer? No? Okay. Gosh, you guys are so shy. Okay. So in the high dimensional case, X transpose X is singular, right? So the minimization, the unconstrained minimization of F doesn't have a unique solution, right? But it is still possible to get a unique solution. It's just not necessarily true, right? If we have the whole problem together. Okay, so let's change our objective function. We're going to change it to this Huber loss, which probably none of you have seen. So before we had like a quadratic-y thing, right? Oh, thank you, Dallas. Okay, so before we had this quadratic-y thing for our objective function, Huber loss, maybe it's easy for you to tell from the thing, is going to be quadratic between delta and minus delta, and then it's going to be linear beyond. Just like an interesting point. Why might we want to use this loss function instead of just a quadratic function? Does anyone have any idea why it might be more useful?
It doesn't go to infinity as quickly.
That's right, that's right. So if I have some big outlier, it's not going to do crazy stuff to my objective value. So that's pretty nice. So is there any answer that changes, right? So what did we say? We said that it is a convex problem, and we said that when n's greater than or equal to p, we have a unique solution, and when p is greater than n, we might, right? So do any of those answers change when I have this new objective function? Anybody? Okay, well, how do you feel about that n greater than or equal to p now? Right? Do I now have the same kind of properties? Based on what we've gone over in this class, do I have the same kind of properties as the quadratic function? Okay. The answer is no, right? I don't necessarily know for sure that the function that I have now is going to be strongly convex because of this linear wing. Now you might observe, right, that it is strongly convex in this window right here, but that's kind of beyond the tools that we've gone over for the class, proving that that would have a unique solution. Are there any questions about this? Okay.
So, excuse me?
Yes.
So it is convex, but it is not strongly convex.
That's right, and it's not strictly convex either. right? Because it has this affine portion, or linear for, whatever definition. So we've lost, based on the definitions we've covered so far in the class, we've lost the guarantee of a unique solution. Okay? So here's another problem that you guys are probably really familiar with, support vector machines in like the slack variable formulation. I think it's clear what the constraints are, right, and what the objective is. So is this a convex problem? Yes. Okay, great. But is the solution unique? I'll give you a hint, like is the solution for the xi i's unique? Necessarily. No, right? Because I have just normal convexity there, regular convexity. But if I change the objective to this, would I get a unique solution now? I would, right? Because now I have something that's strongly convex in all the variables that I'm minimizing. But I'm probably not going to get the same separating hyperplane. That is a really weird objective function to use. Okay, so let's review. Why do we care so much about strong convexity, strict convexity, whatever? Because it gives us these wonderful guarantees, which is that if we have minimized the function within some ball, then we're guaranteed to have minimized it over its entire domain, right, over the entire feasible set. And this is really nice because it tells a lot of the algorithms that we're going to learn in this class when they can stop. So that's a really nice property of having a convex function. Yes?
This applies to both the strict convex and the non-strict convex.
Yeah, so regular convex functions, right, if I find a local minimizer, it's going to attain the global optimal value. But if I have a strictly convex function, then there's only going to be one such point, right? But the good news is f star is going to be, so if I have multiple solutions, f star will be the same for all of them, right? That's the nice property of our convex problem. Okay? Any other questions? Yes?
Can you run the differences between the strong and strict?
Yeah, so I don't have my the last lecture slides up. But if you go from, so regular convex, normal convexity, I don't know, these terms all have loaded math meanings. Okay. Can you see what I'm writing? Am I still good? All right, awesome. So with simple convexity, this is a less than or equal to, right? And this is just saying that any line I draw, oh, I'm off the screen. Okay, any line I draw that's connecting 2 points is going to be above my function. But if I switch to strict convexity, then I'm actually making some guarantees about the curvature of the function. So this becomes a strict inequality, right? And that means that not only do I have this property of the line at the very least being on my curve, right? It's always going to be lower bounded, okay? So that just is kind of like a stronger statement about how flat the function is near its minimum in some ways, right? So a quadratic function is not super flat near the minimum, but then if I have like x to the fourth, right? What happens to x to the fourth? It sort of flattens out like this, right? So strong convexity, which is something that x squared has, is saying that this is curvy enough that I can always be sure that I'm connecting 2 lines above my function. But regular convexity just says, well, sometimes this line can lie on the function, right? And I don't have the formal definition for strong convexity up, but the most important thing to remember is strong convexity implies strict convexity implies regular convexity. Okay? Does that answer your question? Sorry, I don't have like last lecture slides up right now. It'll take me a little bit to find them. Okay, so if we're all good with that material, let's move on to some things we can do to make convex problems easier to solve, or any optimization problem. The first thing to realize is that the feasible set can be described in set notation, which is nice, right? So I can take my function f subject to these constraints and then change it to say, okay, I'm minimizing f subject to x being in this set, where the set is defined by my constraints. That's really nice. But maybe that's not a huge difference from what we had before. What is kind of interesting is that now we can add an indicator function to f instead, and suddenly we have an unconstrained minimization problem. So recall what the recall what the indicator function says, right? It's going to be 0 if x is in C and infinity otherwise, right? So this is the same thing as saying, well, it's going to be impossible to minimize my function unless x is in the feasible set. And you're going to see methods that we learn, like barrier method, for example, are going to make use of this idea, right, to do a better job optimizing problems, okay? Are there any questions about that? No? Okay. Okay, so what are the properties of a solution to a convex optimization problem? So if we have a feasible point and f is differentiable, we can describe optimality in the following way, right? The gradient of f times y minus x is greater than or equal to 0 for all y in C. To summarize that in words, it means moving anywhere from where I am is only going to make my objective increase. That's basically what this is saying in words. So to give you an idea, right, I always do quadratic functions, I guess. To give you an idea of what that means, if I have this simple function, right, I'm at x, I'm at the minimizer. Anywhere I go in the feasible set, which in this case is just r, right, the gradient, the derivative, is going to be positive, right? And so that way, I'm always going to know that I'm increasing my function. Okay? And you can see how if we're not worried about feasible sets, right, and we're just doing an unconstrained minimization, this is going to reduce to something that is very familiar to all of you, like a very familiar property of convex functions, which is that the gradient is equal to 0 at a minimum. And you can actually derive that from the above, right? So from this guy, what you should do is if you let y equal x plus or minus ei, where that's a standard basis vector, right? It's 1 on one dimension, on the ith dimension, and 0 elsewhere. Then what you wind up with is the ith element of the gradient has to be greater than or equal to 0, and the negative ith element of the gradient has to be greater than or equal to 0. So you can do this for every element and show that they all have to equal 0. Okay? So does anyone have a question about that? Just like using kind of simple properties. So all the formulations that we're going over right now are pretty general, right? We talk about optimization problems over a feasible set, but they do generalize to the calculus that you've learned before. Okay, so let's look at an unconstrained problem. We've actually kind of thought about this. Yes?
To be able to do this thing, we didn't really need the entire domain, right? We just needed to be an interior point.
Right, so yeah, so if C is spanned by these basis vectors, is that what you're saying?
I'm saying that what you have done is just move from x in all possible directions and find a y, right?
That is correct.
So you don't really need the entire Rn.
No, you don't. But it's pretty rare that C will be such that you can still do this argument. It might be true, but it will be rare.
You need this to hold for all y inside the feasible set C. So if the optimal solution is on the boundary, you don't need to search for any direction, only those directions in the set.
Yeah, so another thing is that the standard basis might not be a sufficient basis for C, right? Like, and then in that case, but we might still be operating in Rn. So then you can't use this argument at all, right? Pardon? Because it's a dot product, right? So we're just, so if I want to travel along a function, right, I'm going to dot the gradient. I'm going to move along the gradient with wherever I'm going. So this is just how we're multiplying the gradient vector with my new point that I'm moving to. Sorry, I don't know if that answered your question or not. Okay, other questions? Yeah.
I don't know if we'll cover this later, but is there a way to apply the calculus we know to the indicator function?
That's a good question. I haven't given that enough thought. I don't know that we're going to cover that later. We are going to cover, when we do interior point methods, kind of approximations to the indicator function that get more or less strict as we optimize. And so then maybe your question will be answered. Other stuff? Nope? Okay. Cool. Okay, so we have this quadratic function, and we kind of already talked about the properties that it has. So here Q's positive semi-definite. So if I take the gradient of this, right, I get Qx plus b. If that's news to you, please review your multivariate calculus. So now it's easier to see the things we were talking about when we talked about the least squares objective in the lasso problem, right? It should be more clear. So if Q is positive definite, right, then we can invert it and we have a unique solution to our optimization problem. But if Q is not invertible, and it just so happens that B is not in the column space, right, then it's impossible to achieve this first order optimality condition. There is no x for which Qx plus b equals 0. So then we just have to resign ourselves and say it's negative infinity. But if B is in the column space of Q, then we can take the pseudo inverse of Q and solve this problem. Okay? So you can see how a quadratic function, when we minimize it, it's either going to have, depending on the properties of Q and B, right, depending on the structure of the function, it's going to have a unique solution, no solution, or infinitely many solutions. So it's pretty important to analyze your objective function carefully, right? Because a lot of the techniques that we are going to learn won't work in that second case, right? Yes?
Yeah, but to be able to compute x equal q inverse, you just need it to be non-singular. You don't need the positive definiteness, right?
So if it's positive semi-definite already, right, at the beginning, then it can still have 0 eigenvalues, right? So what I need is to make sure that none of its eigenvalues are 0. And so the way that we increase, like turn up the heat on the positive semi-definite is to say, okay, now it has to be positive definite, right? Because the positive semi-definite Q could still be singular. So they're equivalent statements. Yeah?
So for this to be convex, does Q need to be positive semi-definite, or is it the other way around? If it is positive semi-definite, it will definitely be convex. Is it two-way implication?
I don't know. I know that it's definitely, at the very least, in the direction of if Q is convex, if Q is positive semi-definite, then it's convex. I feel like intuitively, I feel like it should go in the other direction. It would be weird for it not to, but I don't actually know for sure, so I don't want to say anything wrong. Other questions? No? Okay. Cool. So now let's talk about what to do if we have constraints. So we want to minimize f subject to this equality constraint. If f's differentiable, we can describe the solution in the following way, right? Which is that the gradient f plus A transpose U is going to equal 0. So what does that mean? That means that the gradient f is going to be in the blank space of A. Linear algebra review. Quickly. Anybody? Okay, spoiler alert, it's the row space. Okay. So we can actually go from our original optimality condition and look at it in the lens of this explicit equality constraint, right? So we know that gradient f y minus x is going to be greater than or equal to 0 for all y that satisfy this ay equal to b. We also know that ax equals b is satisfied. So to do this proof, right, and show that this is equivalent to that term with the v in it, so I've got ay equal to b, ax equal to b. I'm just going to subtract them, right? So then now I know that y minus x satisfies this, and I'm just going to name it v because Ryan named it v. And so that is in the null space of A. So if we go back to our first order optimality condition that we learned in the general case, what this means is that the gradient of f dotted with every element of the null space of A, right, is going to be greater than or equal to 0. So actually, if you, let me just check my note to make sure I don't, yeah. So actually, if you think about what you can let y be and still satisfy this, right? If we take a different y and we let it be 2x minus y, right? Okay, let's do this, y prime, right? If we take y prime and let it be 2x minus y, right? Ay prime is still going to satisfy this constraint. Does everyone see why that would be the case? Or does someone want me to go through it? It's okay if you do. Okay, right. So notice that y prime minus x is actually equal to negative v. And because this is still satisfied, right, we actually have the following. Has to be greater than or equal to 0. Okay? So both this quantity and the negative of that quantity have to be greater than or equal to 0. What does that mean? It means that it's 0, right? For all v in the null space of A. So when the dot product of two things is 0, that means they're orthogonal, right? So if our gradient f is orthogonal to every point in the null space of A, that actually puts it in the row space of A. And that's how you can show that this is necessarily true for some u, right? There just has to exist a u. Okay, did people follow that, or was that like a little too fast? Too fast? Okay, cool. So let's just try it like a little bit slowly. Okay. So we have ax equal to b satisfied, right? And then for some y, necessarily this guy is satisfied. So we know that y minus x is in the null space of A. So this dot product is going to be greater than or equal to 0 for every v in the null space of A. So I can find another element, right? Y just has to be in the set of feasible points, right? So I can take another feasible point, but it has a special relationship to the one that I picked before. Maybe let's call it alpha so that it's a little less confusing. So if I let alpha equal 2x minus y, alpha is still going to be a feasible point, right? Alpha is going to be in C. And alpha minus x is going to equal negative v. So because alpha is feasible and my first order optimality condition is holding, right, by picking that other alpha, I can also prove that should be a V, that that's greater than or equal to 0, right, for all V in the null space of A. Okay? So if both of these things are true, then this left-hand side must equal 0. Okay? And that means that my gradient is perpendicular or orthogonal to every element of the null space of A. And that's actually how we define the row space of A, right? The row, or one of the ways you can define the row space of A. And if that is super unfamiliar and surprising, I'm going to suggest that you look at Zico Coulter's linear algebra videos, or even Gilbert Strang has like a really awesome series of lectures that should be up on MIT's website. Okay? Did that feel better? That felt better for me also. Okay, great. Yes?
Did you define alpha as 2x minus 1, or does it come from anywhere?
So I picked a random y from the feasible set, and then I'm picking another alpha, but I'm going to relate it because I want to do this proof. But like this is true. This is true for everything, but I also wanted to show that this is true for all values of y as well. Did that help? Okay, cool. Great. Okay, so let's talk about a problem that maybe some of us have done before, which is projection onto this convex set. And we're going to see that it's related to something that we've already learned in this class. What I want to do in this projection is minimize the distance between the point I'm projecting, A, and the point in the set, X, right? That's going to be the result of my projection. I can use the same first-order optimality condition as we learned previously to get this relationship, which is that X minus A transpose Y minus X is greater than or equal to 0. So let's recall the definition of a normal cone here, and then we'll talk about the geometric interpretation of this result. So recall that the normal cone is going to be the set of all G such that G transpose X is greater than or equal to G transpose Y, X and Y, or yeah, Y in the set. Right? So if we just move everything, you can see that this is equivalent, right? This is an equivalent description of the normal cone. So if I let G be X minus A, or A minus X, sorry, A minus X, then what I've shown is that the first order optimality condition necessarily means that A minus X is in the normal cone of X with respect to this set C. So geometrically, right, when we were going over normal cones, you could kind of see this result coming, right? The normal cone is going to be, for a particular point, is just the set of all points that are closest to it, right, outside of that set. So for these, like, single lines, right, you can tell they'll be projected there because that's the shortest path that they have to go. And then any point in that shaded region is going to get mapped to that corner. Is that clear to everybody?
So
Yes.
where is X and so can you take us
Oh,
to
yes.
X?
So X is actually, I can use my mouse. Okay, so here's X, right? And then these are, so any A within this cone, right, within this region is going to map to this X as a solution to this problem. Like X is the solution for all of these projections. Okay? Other questions? Yes? No? Okay, I thought I heard whispers. Okay. So actually, we're like halfway through. So if you guys want to take a break, because we're going to kind of shift gears for the next bit, this is probably a good time to take like 5 minutes. I don't know. All right. So we actually talked about this last time when we talked about convex functions in general, right? We can always partially optimize a function, and it will still retain its convexity. And that can be really nice, right, for convex problems. So if I can divide the variables that I'm minimizing over into 2 blocks, let's say, I can completely eliminate one and still have a convex problem as a result, right? And sometimes this is easier to do, and there are methods that we're going to learn about that actually will do this kind of back and forth between one variable and the other. Does everyone see that? That follows directly from properties of convex functions that we talked about last time. Okay, so let's look at an example of this, which is SVMs. So some of you maybe are not as used to the top formulation and are maybe more used to the bottom formulation of SVMs, which we call the hinge form. And I'm going to explain a little bit how that top problem becomes that bottom one. So in our initial problem, our slack variables are subject to these inequality constraints, which we can summarize with this max term. So xi I is going to at least be the max of 0 and this kind of loss term, for lack of a better word. So I'm going to argue that if we have the optimal xi I, that's actually going to be an equality and not an inequality. The reason I'm going to argue this is, let's say that xi I is somehow bigger than what's on the right. Then that means that there's a feasible xi I, which is equal to what's on the right, that would be of smaller value than my initial xi I. And if we look at the objective, decreasing a xi I can only make my objective smaller, right? Can only make my objective smaller. So I'm always going to want to move to the point where we have equality. I always want this inequality constraint to be active. And you're going to apply this same line of thinking, here's a hint, to your homework, one of the problems on your homework. So if we know that at a solution, xi I is going to be equal to this quantity, we can just get rid of xi I completely, right? We've solved it. And then that's how we get the hinge form of SVMs. Does everyone feel good about that? That line of reasoning? Okay. So another thing we can do is transform our function or change variables and whatnot. So if I have h and h is monotone increasing, I can apply h to my objective and still have a convex problem. And I don't need to worry about changes to the feasible set or anything like that. Recall, you might be confused by the definition of h mapping from R to R. Recall that we've been thinking only about real-valued objective functions. But a function would still be convex even if it were not real-valued if I applied a monotone increasing transformation to it. So you guys have done that. Can you think of an example where you apply an increasing h to f?
Log likelihood.
That's right, log likelihood, right? When we do maximum likelihood estimation, sometimes we just take the log because that makes everything better. So that's something that you guys are probably familiar with doing. So this also can be used on our inequality constraints and our equality constraints. And that can sometimes make a problem easier to solve or convex when it didn't appear convex before. We're going to see kind of much later an example of this. So another thing we can do is change variables. And this is something that maybe doesn't seem super useful now, maybe seems more trouble than it's worth, but will appear usefully later. Right, so if I have a phi, and phi is going to cover the output of phi is going to cover my feasible set. Are we familiar with the term image of a function? If it's going to cover my feasible set, then I can replace every instance of x, right? I know that for every x, I can find a y such that phi of y equals x, right? That's basically what that statement is saying. Then I can replace x in my convex optimization problem with phi of y, and it's still the same problem. Or, well, it's the same problem modulo a transformation using phi at the end to get back x. Is that clear to everybody? Okay, great. So we're gonna, in a little bit we're gonna go through an example of this, but sometimes, someone is telling you their needs for a problem, right? So I need to minimize this function subject to this constraint and this constraint and this constraint. And that initial formulation that you walk away with is not going to be convex. Like let's say one of the inequality constraints is not convex, or worse, and this is actually the problem that we're going to see. You know, I want to minimize x in some set C, and C is not a convex set for some reason. So if I can do transformation, if I can apply transformations to my constraint set, then I might be able to find a way of formulating the problem so that it's convex in X. That's what it means by finding the hidden convexity of a problem. So Ryan and I decided to skip this example because I think it's a lot of trouble. But if you're interested in how this applies to making geometric programming a convex optimization problem, you can read through these slides. Okay. So other changes we might want to make to a convex optimization problem. We might want to get rid of our equality constraints. And the way we can do that is by applying a very particular affine transformation. Or rather, yeah, I guess you could call it that, but maybe that's not a very precise way to refer to it. So every feasible point x is going to satisfy ax equal to b. Right? So if I let x equal this my plus x naught, where x naught is another point from the feasible set, I know that AMY plus x naught equals b, right? If I let this guy be from the feasible set, then what I have is AMY plus AX naught, which is b, equals b. So my requirement for y, or for my, is that we get kind of a column space, null space relationship. So if I do this transformation, I can always do this transformation, then I can get rid of my equality constraints and still retain the same feasible set as I had previously. This kind of seems like it's more trouble than it's worth. That's because it usually is. But it's important to know that you're allowed to do this. It might come in handy someday. Other questions? No. Okay. Cool. Now something that we do a lot, right, in modifying optimization problems is introducing slack variables. And these get rid of inequality constraints generally. So it should be pretty clear from how inequalities work that this is equivalent to this, right? All I'm saying is that there's got to be some distance, 0 or positive, between gi and 0. And that's basically the same thing as having an inequality constraint. And this is nice if g is affine, right? This is nice because now I don't have any inequality constraints. And you'll see that some methods we go through can only handle equality constraints, for example. But it's really important to remember that g has to be affine in order for this to help you retain the convexity of your problem. Does everyone see why that has to be? Right? Because our equality constraints need to be affine? Okay. Any questions about that? Yes?
You did introduce new inequality constraints.
Yeah, but that inequality constraint is usually, this is much easier than having g of x less than 0. I'll put it that way. I don't want to go too far on that because we will solve problems where we make this change and then it will be more clear kind of how that helps. Yes?
So do you not need to analyze the slack variable in the objective function?
No. I see. So in SVMs, right, the notion of slack variable is a little different than the notion here, right? In SVMs, slack variables kind of tell you how many errors you're allowed to make or something like that. They have a kind of semantic meaning that's related to the objective you're trying to minimize. These slack variables are just a simple modification of your inequality constraints. But I can see that it's a conflating of terms, right? The same way that a transformation of G would not change my objective function, this also does not change my objective function. Is that cool with everybody? Okay, awesome. Okay, so now what do you do if you have the misfortune of being posed with a non-convex optimization problem? One of the things you can do is relax the problem. So you want to minimize f subject to x in some non-convex set C. You can always find a convex set that covers C, right? What set would that be? Like, what's the logical one?
Convex hull.
Yeah, the convex hull, right? So that's kind of an easy relaxation. It's possible that you might not want that particular C tilde, but it's always a good one to try, right? So if I have equality constraints and they're not affine, which makes my feasible set non-convex, the easiest way to relax them is to just replace equality with an inequality, right? So long as h is a convex function. If it's not a convex function, then I don't know how to help you. And sometimes this is really nice because you have a problem that's tractable or easy to solve, and you'll still get the same solution. There are certain problems that have this property. And so here's a problem, and it's on your homework, that has such a property. This is called the maximum utility problem. And the idea is, at time t, I have some budget, bt. And I go and I invest that budget, and I get some return on my investment. That's f of bt in the above formulation. And then my initial budget and my returns on my investment form how much I can spend on that turn t. So I spend some of it, xt, because it gets me some utility. That's the u function. So if we assume that u is convex, right, and f is also a convex function, do I have a convex problem in this initial formulation? Just shake your head or nod or whatever. You guys are so shy. Okay, this is not convex, right? Because my equality constraint is not affine. F is not affine. I just told you that it's, oh yeah, okay, it's concave and increasing. Sorry, because we're doing maximization. Just think of u and f as being concave. So in your homework, what you're going to argue is that relaxing this non-affine equality constraint to an inequality is a valid thing to do and will still get you the same solution for your budgeting problem and your spending problem. Okay, and we've kind of gone through the logic of how you might think about that before, right, in the SVM example. So this should be pretty doable. Are there questions about like the maximum utility problem in general? Nope. Okay. So that's an example of a problem where you can relax it and still get the original solution. Here is another.
How do you know that you get the same solution?
So what you're going to argue is that at the solution, at the best b and x, this is equality. The same way that I argued for the slack variables in the SVM example, that at the solution you would have equality. You're going to do that here. And that tells you that you are going to have the same solution to your problem because it will satisfy the original constraint. Okay? Swell. So here's something that you're all probably really familiar with. Maybe, actually? I don't know. We call this principal component analysis. Often we have some matrix X, and we want to find a matrix R that's close to X but is low rank because that's a lot easier to work with for other applications, right? So we can frame this right off the bat, if you just go by what I said, as kind of a least squares loss, right? We want to minimize the reconstruction error from R to X, subject to the rank of R being equal to K. So the set of all R such that the rank of R is equal to K for some K. Is that a convex set? No, right? It's not a convex set. Does anyone want to hazard a counter example, like why it's not convex? Okay, I can do kind of a small one. So let's say K is 1. So I can have this matrix, right? These are all zeros. And then I can have this matrix, right? If I add them together for any value of theta between 0 and 1, I'm actually going to get a matrix with rank 2, right? Because it'll have 2 non-zero diagonal entries. So convex combinations of rank K matrices are not necessarily rank K. So this is a non-convex problem. But we still know how to solve it, right? You guys have probably done this before when you want to do dimensionality reduction. You get the singular value decomposition of X, and then you just take the first K singular vectors, et cetera. And that will get you a reconstruction, the best reconstruction of X that's rank K. People have maybe seen this before. We call these K vectors, by the way, the principal components. Same language. Some people say PCA, some people say SVD. So let's make this a convex problem. And we can actually do this, right? Which is pretty cool. So the first thing we're going to do is rephrase this as a projection. There are some good properties of projection matrices. If they're like, out the window, don't stress. We're going to be okay still. So if I express our original problem like this, what I want to say is I want to find a z that projects x in such a way that x's original form is somewhat retained, right? We still have our least squares laws. And controlling the rank of z is actually sufficient, right? If r is xz, then controlling the rank of z will still get me k for r, okay? But the nice thing is when we put this in set notation, so z's got to be a projection matrix. Each eigenvalue of z is going to be either 0 or 1, and then the trace of z is going to be equal to k, right? So this is still non-convex. Does anybody see which part of these 3 sort of requirements on z is giving us issues?
0, 1.
The 0, 1, right? That's a super non-convex set. And also, just for your knowledge, the solution can be written in terms of the singular vectors, just like that for z. Okay. So let's do what someone suggested earlier, right? And take the convex hull of that set C that I just went over. So what is the convex hull of it? It's just letting that 0 or 1 relax into the range of 0 to 1. And this is you can get this from the definition of the convex hull. Is that clear to everybody? Okay. So if that's true, then this should look familiar, right? This is a structure that we learned in lecture 2, which is just the fantope of order k. So you should go back to your lecture 2 slides if that word sounds like mumbo jumbo to you. And then now we can minimize this function, this least squares loss with respect to z being in the fantope of order k. And this is easily solved, right? This is a convex problem. And this will give us the same solution, in fact. The proof is beyond the scope of this course, but if you want to read it, it's this really, really old paper. But that's how, even if you have something that's non-convex from the outset, you can still transform it into a convex problem that has an equivalent solution to your original non-convex formulation. Okay? Does everyone feel okay about that? Okay. So actually, I went a little bit faster. So that's all I have. If you have more questions, you can come up and ask me or whatever. Thank you, guys.